Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillah rabbil alamin wassalatu wassalamu ala rasulillah wa ala alihi wasallam. So this is lecture 4, which covers the stress transformation using Mohr circle, where we will learn how to draw and interpret the Mohr circle for plane stress. It's going to be a quite long lecture, but I hope you can take it slowly, and please rewind when you do not understand, and okay, throw me the questions back to me via the email. These are the YouTube that I think you can watch. There are plenty more YouTubes. I think Mohr circle or stress transformation is one of the most well covered topics in YouTube. Okay, so let's start. So there is no normal component to the shaft. So for example, there is, when I say normal component, this is the, let's say there is a stress there, and where you need to show this is a stress, and that's not a plane stress. So a plane stress is where you don't have a normal component. So I'll just remove this blue thing. Yeah, so it's not that. So example of plane stress is, for example, this shaft when you subject it to, and you can find the stresses acting on the surface of the skin of the shaft. So this is called plane stress, and if it is a 3D, it's not a plane stress. Okay, so stress transformation is a transformation equations for plane stress, which can be represented in graphical form by a plot known as Mohr circle. Yeah, and what is this Mohr circle? It is a graphical representation to visualize the relationships between the normal and shear stresses acting on various inclined planes at a point. And it is used to calculate principal stresses, maximum shear stresses, and stresses on inclined planes. So most of the time, we are basically interested to find the principal stresses and the maximum shear stress. And sometimes we also want to find the stresses at other angles or other orientation. So that's what stress transformation is all about. So when we say transformation, is we want to find what is the normal and shear stress acting on various inclined planes. So what is the normal and shear stress acting at various inclined planes at a point. So this is a stress transformation equation. I will not show the derivation of this equation. There are two equations here. The first equation is for the normal stress in the x1 direction. The second equation is for the shear stress acting on the x1, y1 plane. So let me make it clear to you. So sigma x1 is the, let's say we have to start with this, start here. Okay, this is where we start. Right, let's say we have a stress element, and where the normal stress in the x direction is given by sigma x, normal stress in the y direction is given by sigma y, and the shear stress acting on the y line, normal to the x, is tau xy, and then the shear stress has got to be balanced with tau yx, and then head to head, and then tail to tail. This is balanced, so the summation of moment about the centroid is 0, and summation of force is 0. So we've got sigma x on this side and sigma y on this side, so it's balanced. Yeah, so you understand how to draw this element. If we were to rotate it, rotate the element, by an angle theta, we will have this kind of arrangement. So suddenly the shear stress acting on that rotated element is called sigma x1, which is normal to the surface inclined at an angle theta, sigma y1, and then tau x1 y1, and these are the three things that we need to find, and this is given by this equation. So you want to find sigma x1, which is the normal stress there, is given by this function. And you want to find the shear stress at this surface tau x1 y1 is given by this equation. So equation 1 gives you sigma x1, the one in yellow, and tau x1 y1 give you the shear stress on this surface inclined surface, and you can find that based on your input or initial conditions. So this one in blue, sigma x, sigma y, and tau x1. So this one in blue, sigma x plus sigma y over 2, sigma x, sigma y, and then finally the shear stress at that particular point. Yeah, similarly you can find untuk shear stress tau x1 y1 from sigma x, sigma y, and tau xy. So the blue ones means that you will just follow where you get this value from. Okay, and tau is here. What about sigma y? So somebody else like, what happened to sigma y1? So let's write it here. What happened to questions, what happened to sigma y1? Okay. So the same kind of answer, only that we have to find it is use equation 1 for sigma 1, or let's use blue or black for sigma y1 equals to similar equation, but we will have to submit theta with 90, you have to rotate by 90 degrees, so 90 degrees, yeah, 90 plus theta, 2 degrees plus theta. Okay, everything else is the same. Okay, so it's just that the theta values changes with sigma y1. Okay, all right. So that's stress transformation. So with now, so what happened here is that, as you can see here, you can now find, as we rotate everything in the angle theta, it will now give you the influence of the angle. Okay, so derivation of Mohr circle based on that equation, based on the equation before, number 1 and number 2, if we vary theta from 0 degrees to 360 degrees, we will get all possible values of sigma x1 and tau x1 y1 for a given stress state. So if you eliminate theta by squaring both sides of equation 1 and equation 2 and adding the two equations together, you will have this form of equation. So if I can draw these lines here using a red pen, yeah, so this equation is clearly in the form of something like called the Mohr-Circle equation. Yeah. So in that Mohr-Circle equation, if we define the average stress as sigma x plus sigma y over 2, okay, if we define average as sigma x plus sigma y over 2, or the mean stress of phase x and phase y, or direction x and direction y, and then we have the r as a function of sigma x minus sigma 2 divided by 2 square plus tau xy square, and then we substitute for the average and r to get in this form. So we will have what is called the Mohr-Circle form of the equation, similar to a circle equation, which is like x squared plus y squared equals to r squared. And that's why they call it the reason why they call it Mohr-Circle is because of that, because of this equation in a form of circle. Okay, so our job is just now to draw the circle and find the relationship, if there is any relationship. So the circle with that equation is called the Mohr-Circle, named after the German engineer Otto Mohr. He also developed the graphical technique for drawing the circle in 1882. So it's almost 200 years. So the graphical method is a simple and clear approach to an otherwise complicated analysis. So it has been around for some times, and people found that it's easier for us to understand plane stress transformation using this Mohr-Circle. So again, I just put it there. Why do you call it Mohr-Circle? Because it is similar to a circular equation for a circle in the xy coordinate. So this is the sign convention for the Mohr-Circle. So there is a sign convention that we have to follow when we want to draw the Mohr-Circle. So we will follow this sign convention. The Mohr-Circle equation is given by this one. You'll find the average and the sigma x and tau, and there's a circle that you need to produce with r. So the first one is that the shear stress is plotted positive downwards. So the Mohr-Circle, they have got two axes. The horizontal axis is for the normal stress, and then the shear stress is positive downwards, and then theta on the stress element equals to 2 theta in Mohr-Circle. So this is the sign convention. If you look at this element here, the positive for the normal stress is tension. So all stresses that is in the tension side for the normal stress is positive, and then both for the x and for the y. And their shear stress is considered positive counterclockwise on the xy surface, on the x-axis in the direction of y. So that's why we call it tau xy. X-axis in the direction of y, it is taken as positive as counterclockwise. So maybe we'll highlight it here. This is positive. So can we write it? So we see it is positive counterclockwise. Okay, so only for this surface. So once you identify the convention for this surface, every other surface will follow through, because they were head to head and tail to tail. So here is the case. So I'm just going to highlight this, that the shear stress tau x1 is positive counterclockwise. Okay, and then the normal stress, let's draw in green. Okay, this normal stress is positive tension. So let's write it. This is positive convention. Yeah, so if we were to draw that in yellow, so we'll say that it is, or green, so it is positive intention. What else? So your theta will follow the same theta. So the other one is that if you have theta on the actual scale, it is translated as 2 theta in the Mohr scale, in the Mohr circle diagram. And then what else? So this is positive downward. I don't think that's a big problem here. This is positive downward. So I think we are ready to draw. I think this is shear, not shear stress, but shear stress axis. Okay. Right. So that's the sign convention. Positive counterclockwise and then positive downwards. So here is the surface. For example, look at surface A, point A. So surface A here. I'm looking at A here. Okay. So you have sigma x positive and tau xy, which is counterclockwise to the centroid of the element. So both are positive. So tau xy positive down here, okay, which is given by this value. And then we have got sigma x as the xy coordinate. So your coordinate here is sigma x and tau xy. So we can write the coordinates of this surface as can we make it bigger? So this sigma x tau xy. Similarly, looking at B, I'm looking at B now. So when you look at B, the coordinate of B is sigma y. Sigma y, where is sigma y? This is sigma y. Yeah, sigma y. And then the y-axis is given by negative tau xy. So this is positive, then this one is negative. So here is, on the top here, you've got B, and the difference of theta, the difference of angle of theta, here is, if you look at the theta here, the angle here, what is the angle here? This is 180 degrees. And this is similar to 90 degrees. If you plot this theta here, it is 90 degrees. So it's 2 theta from here to theta. Here is 90 degrees. 90 times 2 is 180 degrees. So this is point A for surface A, point B for surface B, or for this line B here. And you've got 2 coordinates. So I will write the coordinates here. This is sigma y negative tau yx. Okay, so, or tau xy. So, yeah, the values is the same. And then the average stress is sigma x plus sigma y over 2, which is C. This C is sigma x plus sigma y over 2. Yeah, so this gives you the average stress. So OC is given by sigma x, this distance here is sigma OC is the average sigma, and R is given by sigma x minus sigma average, this distance, sigma x minus sigma average square plus tau xy square. Yeah, and you find that square root of all. This equals to R square. So I'm looking at the Pythagoras theorem here. Like, look at this, R equals to this sigma x minus sigma average square plus this tau xy square. So this is so that's the circle equation for the Mohr circle. right? So how do we then have a formal procedure of constructing the Mohr circle? So the procedure is draw a set of coordinates uh, of normal stress, normal stress, normal stress, and tau y. So what do? You draw a coordinates axis system. So this is normal, and this is tau. This is tau positive. So this is this is positive. This is positive. So that's number one. Point A on the stress of the x element. So you will. This is if you have any stress. So sigma x and sigma y, and this is tau x in the y direction. So you can now draw that point. So point A is sigma x plus tau xy. So let's assume it's all positive. So this is point A. So that's point A is sigma x tau xy. And point B is also positive. So unless it's negative, you have to go on this side. So this is 0, yeah? So still positive. So let's say because the tau xy is still the same. So this is A and B. Yeah? This is point A and point B. Right? And then the middle one, this is C, which is the average. And from there, this is your R. So you can draw this Mohr circle here. Okay? So that's the way. So draw a line from A to B. This is your line. And this is OC, is the center. And you have coordinate. This is average coordinate, as we have done before. This is sigma average. And then you got the radius of the circle. So radius you can calculate using Pythagoras theorem. And then this is how you construct the Mohr circle. We have done it before. This is just a way of repeating that technique. So explanation. On the Mohr circle, point A corresponds to theta equals to 0. Thus, if it's the reference point from which angles are measured, the angle 2 theta locates the point D on the circle, which has coordinates point B actually. It's not point D. On the circle which has coordinates sigma x1 and tau x1. D represent the stresses on the faces of the inclined element. Point E, which is diametrically opposite point D, is located 180 from CD. Thus, point E gives the stress of the y1 face of the inclined plane. So, as we rotate the xy 1y axis counterclockwise by an angle theta, the point on Mohr circle corresponding to the x1 face move counterclockwise by an angle theta. So principal stresses are stresses at the extreme end. These are called principal stresses. And what happened at principal stresses is where the value of tau is 0. You are along this line, and so we can find sigma 1, for example, is equivalent to OC plus R. And sigma 2, the minimum stresses, is OC minus R. Where is OC? OC is here. This is OC. And R is given there. So, and what is tau max? Tau max is also known as equivalent to R. And how do we get R? R is by finding the previous technique. We can find what OC is, what R is. So we know that OC is the average. So sigma x plus sigma y over 2. And then R is equals to the difference of sigma x minus sigma y over 2 squared plus tau xy squared. And then you can use that Pythagoras theorem to find your value of maximum and minimum stress. And these are called principal stress. Again, it is called principal stress. Okay, where you value as sigma 1 or sigma 2. You look at here, this is sigma 1 and sigma 2. Okay, so Principal stresses are stresses, explanation, are stresses that act on a principal surface. This surface has no shear force component. That means the tau x1, y1 is equals to 0. This can be easily done by rotating A and B to the sigma x1 axis. So sigma 1 is the stress on x1 surface, sigma 2 is stress on y1 surface. The object in reality has to be rotated at an angle theta p. Theta p is called the principal angle to experience no shear stress. Okay, so again, the explanation is like this. If you have this element, right, this is sigma x, this is sigma y, and you got tau value there, tau x, y. And what happened is that we will now rotate this element at an angle. So you incline it to an angle, for example, theta p, we call it principal stress, where the value of the tau, value of the shear stress is 0. And we can now label that as sigma 1 and sigma 2. Yeah, so this is called a principal plane, principal angle, theta p. Okay, so that is what happened. So what we did was we rotated this by theta. So how it looks on the Mohr circle is that it will look like this. Sorry. So on the Mohr circle, it will look like this. So when you draw, this is the stress element. Okay, and let's say this is your point A. So sigma x, tau xy is your point A, and you've got point B here. This is sigma y, tau xy. This is positive downwards, tau sigma. And you got also your, this is your centroid C, OC, and you got your circle here. Okay, and this is your position of stress 1 and stress 2, maximum and minimum stress. So in the Mohr circle, this angle is 2 theta, which corresponds to the angle of theta here. On the Mohr circle is twice that angle. So what happened here, this is where your theta is like this. This is where there is no shear stress. Shear stress is 0. Only the element here at surface A and surface B have sigma 1 and sigma 2. So that's how in reality is theta. In reality this is theta. Yeah. In Mohr circle is 2 theta. So let me make it larger, 2 theta. So that's how you link. With several exercises, I think you will get it more clear to you. Okay. So maximum shear stress, as we have repeated, told you just now, is tau max equals to the shear radius. And at this point, what happened is that at maximum shear stress, when you are here, this is point of maximum shear stress, we will still have your value of sigma x and sigma y, but your shear stress is the maximum. Okay, so this is the location of maximum shear stress, so-called 2 theta s. It's not that significant, but if you are interested to find the maximum shear stress, this angle is equivalent to that angle. Okay, and the direction can change as you rotate. Just now it was positive counterclockwise. Now at this surface maximum shear stress, we can see that the shear stress is now changing direction to clockwise. Okay, this is a general observation. It depends on the stress condition of the element that we constructed. So the explanation is that the same method can be used to calculate principal stress to find the maximum shear stress. Points A and B are rotated to the point of maximum stress value. This is the maximum shear stress value, which is tau max. Okay, So uniform planar stress, sigma s, and shear stress will be experienced by both surfaces. So in reality, you have to rotate the angle by theta s to experience maximum shear stress as shown earlier. So this is one example to draw the Mohr circle of the stress element shown below. So to determine the principal stress and the maximum shear stress. So if we follow the technique before, I will just draw. The first one is we draw the axis. So that is the sigma axis, and this is the tau axis. So what is the coordinate of A? A is negative, A is 80 compression, okay, and 25 in the clockwise direction. So I can say that A is minus 80 and also minus 25 because this is clockwise, yeah. So what about B? What about B? I can say that B is positive 50 and then it is positive 25 in the shear stress. It must be balanced, okay. And these are just the two coordinates that we need. So if we draw that, we need to adjust this position again, this theta position. So if we draw that here, tau. So we've got minus 80, so 20, 40, 60, 80, this is minus 80, this is 0. And then we've got 20, 40, 60, 80, this is about 50. So this is positive 50. And we've got 20, 40, this is positive 20. And this is line of 25, for example. This is okay, negative 20, 40, so this is line of positive 25. This is negative 25. So this is positive 20. This is negative 25. Negative 25. So to sketch, so it's minus 80 minus 25. It's here. This is my point A, and point B is positive 50 positive 50, positive 25. So my point B is here. So I can find this is, I can draw this, my C is here, centroid. So this is, and then from there I can draw the circle, lebih kurang lah ya. So this is how my circle looks like. Ya, tak cantik. But we can do the calculation here, like OC is the average of the mean stress, so minus 80 plus 50 divided by 2, so minus 30 divided by 2 is minus 15. So I know that my location here is OC minus 15 megapascal. My R is sigma x minus sigma y, the differences, and then divided by 2, okay, and then times tau square. So these are the sigma x minus sigma y minus 80 minus 50 divided by 2 square plus tau. Tau is 25 square. Okay. So 80, 50, 50, 130, 75, 65, 130, 65 square. 65 square plus 25 square. Square root. Okay. So these are the value I have to, so you can find that sigma 1 equals to OC plus R and sigma 2 is OC minus R. Okay, can you do that? Yeah, so if you do that, you will find that the solution is given. Okay, 69.6 megapascal, and then your C average is minus 15 megapascal. So you'll find that OC sigma 1 is OC plus R equals to OC is minus 15 plus 69.6, and sigma 2 is OC minus R minus 15 minus 69.6. So that's your answer. Yeah, please put the unit at the end. Okay, so you will get your answer at sigma 1 54.6 and sigma 2 minus 84.6 megapascal, and you can find the angle here, theta 1 and theta 2. Your theta 1 is, you have to rotate this by theta 1 and theta 2 by 10.5 degrees to get your theta 1. So theta 1 is here. It has to be rotated about this angle. That not much actually. Theta 2. So 10.5 degrees plus 90 become 105. So this is how you rotate the element. Okay, so you can do the calculation by now. I don't have to show to you all the details. And then you can find the maximum shear stress is equivalent to the tau max equals to R, 69.6 megapascal, and that the stress at the condition where shear stress is maximum is given by minus 15 megapascal is OC. The maximum stress at the condition where shear stress is maximum, and this is the angle, again 2 theta equivalent to theta here. And you can look at the taking sign convention into account. Yeah, please go in details. As a moment for you to do self-learning here. So this is an example 2, and I will cover that in the next lecture. Thank you very much. Bye bye. Assalamualaikum warahmatullahi wabarakatuh.